And it turns out one of the common side effects of being popular with your students is that many of them will want to work with you. And so in the aftermath of that class, you got a bunch of new rotation students, including myself. It turned out, after I started working with him, that I'd actually known about his research for a long time in advance of that through popular press coverage of some of the things that he and his students had worked on. Broadly speaking, Jim's work may be characterized as statistical mechanics, but it often has a surprising twist. So, for example, some years ago, one of his students discovered that there's interesting collective behavior in mosh pits at heavy metal tables. They were able to reproduce some of their interest in collective behavior through simulation. And that got a lot of attention. Another thing that happened a few years ago, they got a bunch of media coverage for modeling how a zombie infection would spread across the United States. And it turns out the statistics of that are in the same universality class as percolation, if you were wondering. On the more traditional side, Jim is one of the founding fathers of crackling, the study of crackling noise, and he still thinks about things in that vein. He tells me recently he's been thinking about renormalization group ideas and how to apply that to crackling noise in 2 dimensions. Today, however, he's here to tell us about sloppy models, which are another very cool idea of his, of general interest both to physicists and to practitioners of other fields. So please join me in welcoming Jim Sethna.
So I'm going to give a talk on sloppy models. I think I gave this same talk here many years ago, a different version of the same topic, but some of the transparencies are the same. And I was also invited by the graduate students, which is very cool. And none of those graduate students, hopefully, are still here. Those of you who are professors who were graduate students at the time, great. It all started when 2 of my students started dragging me to talk to cancer biologists about what later became called systems biology, where I'll describe our model of the cell. I'll describe how we could not figure out what the parameters were given the data, but yet we could make predictions, and that's I'll describe as sloppiness. I'll give you some simple examples of sloppiness. I will then morph into differential geometry, which we use to explain sloppiness, introduce hyperribbons, give you some really cool applications where you can actually use the geometry of multi-parameter models to develop coarse-grained models. I'll have a little bit of replica theory for those of you who know about that. I'll have a little bit of a normalization group. That's going to be this afternoon. Okay, so roughly speaking, I'm fitting models to data. The classic problem in fitting models to data is radioactive decay, where you mix up some radioactive elements and you watch the decay, and you take measurements, and you try to figure out which elements were there. This is known to be an incredibly ill-posed problem. That you have 6 parameters if you have 3 elements and 3 unknown decay constants, and you can get really quite good fits with an enormous range of parameters, and that enormous range of parameters prevents you from making any predictions outside the range of data. So the model can be good at interpolating, can be terrible at telling you anything about what the actual microscopics is, and if you try to make predictions outside its realm, it can give you bad errors. Roughly speaking, I'm going to now take that basic simple idea and turn it into a general principle whenever you have multi-parameter models. So roughly speaking, I'm going to have parameter space and behavior space. And there will be some combinations of parameters that you can only vary a little bit without screwing up the behavior. And other combinations of parameters, most combinations of parameters, many linear combinations, which are sloppy, which you can move a great deal without changing the behavior. So there's this skewness in the mapping from parameter space to data space that it's at the root of the geometry of the problem. Cool? So this was the model that my cancer biologist wrote down. He's not a traditional cancer biologist. He came from a chemical engineering background. He's used to differential equations. And roughly speaking, he just after a bunch of false starts, he drew this diagram, and we said, well, what are the differential equations? He said I could write them down. He wrote them down. You can't read them. They're too small. You can blow one of them up, and it's this. And so this is d, one of these things, dt, is rate constants and rate constants and rate constants, and it's a nonlinear differential equation. These are called Michaelis-Menten equations, and they're very popular among the biologists, and they simplify an even more complicated equation. And there are now 6 rate constants and saturation constants. And all told, there are 48 such constants. And we asked him, so we can type in differential equations, and we can even type them in so that they all balance. If we're clever, and so that it can produce LaTeX output automatically. But we need to know what these constants are. And he said he didn't know what they were. And we said, well, can you give us a range? And he said, I could give you a range within maybe 3 orders of magnitude. And then we said, well, can't you measure them? And he said, it would be too boring. I couldn't hire anybody. And if I did hire somebody, they'd never get another job. Turns out he was absolutely right, that knowing all but one of these rate constants, even if this were exactly the right model, would still give you very little information about the behavior. It's fascinating that the biologists have common sense. So what I'm going to describe is not just the best fit of all these parameters, 48 parameters. I insisted it was going to be very important not to just think about the best fit, but to ask, if you had almost as good a fit, would you still be able to make any predictions? And Boltzmann and things. But one thing I wanted to say is that one of the key questions is if I ask for the quality of the fit, here are data points, here's the model prediction, here's error bars, I can ask how this cost, this chi-squared, varies as I change my model parameters. And that gives me some Hessian. And I'm going to have stiff directions of that Hessian, stiff directions and sloppy directions in that Hessian. And I'm going to, I used to call these eigenparameters and bare parameters, but these are the linear combinations that matter, and these are the linear combinations that don't matter. I'm going to spend a lot of time talking about those eigenvalues. The eccentricities of these ellipses are the square roots of those eigenvalues. Okay, so we took our model, we fit it to data, and then we looked at the fluctuations in the various parameters. So some of the parameters varied more than others in the ensemble that all fit the data. So all these parameters fit the data, and these parameters could be varied by a factor of 500,000 and not change anything. Well, it's not that I can change this parameter by a factor of 500,000. I can change each of these parameters only by a factor of 2 or so without screwing it up. But I can change this one by 500,000 and change others by other factors and compensate. The best known parameter in this ensemble varied by a factor of 50. Okay, so this is really what I was bothered by. I was thinking that this was going to be hopeless, and this looks hopeless. It's not quite hopeless, because of course these are the bare parameters. If I look at the eigenparameters, if I look at the stiffest direction, the ensemble that we used, the stiffest direction only was pretty well constrained, and the second stiffest direction might have gone up and down by a factor of 2. So there are 4 or 5 stiff linear combinations that may be in this ensemble. Those combinations can't be changed very much without screwing up the fit. Now, then the question was, could we make any predictions? Was this model, after we fit all this data, useful? And these days, everyone knows that systems biology is a big field, and lots of people build these models. But at the time, I was kind of skeptical. And sure enough, our ensemble made definite predictions for a particular experiment where we would block this protein in the network and try to see what happened. And this experiment, if you stimulate with EGF, you got a transient response. You stimulate with NGF, you get a sustained response. That difference was very important. One of them caused the cell to turn to a neuron. The other one that caused it to replicate. And this output, if you knock this out, it stayed roughly the same. This was opposed to my colleague's suggestion. He thought that this part of the network was crucial for turning off this signal, and our computer told it that it didn't matter. And sure enough, the computer was right. Now, that's not why I think this is such an important slide. The fact that we can get a yes-no question correct should be thought of as a 50-50 chance, except that my colleague Rick Serione is almost always correct. The thing that's exciting is that, look at these error bars. This is 1 sigma, but still, these error bars are the ensemble prediction of the same ensemble I showed you in the previous slide. That each of the parameters, the best known parameter, was varying by a factor of 50 here. That the collective behavior of this network didn't care what the parameters were. It only cared about that all of this particular experiment is clearly an interpolation, not an extrapolation. The fact that you didn't know what the model parameters were didn't prevent it from giving you correct answers. And there are lots of other experiments we can do here that are clearly also getting the right answer because they too are interpolations. We then started looking into why this was true. So you remember this Hessian. This is the fit of decaying exponentials where it was easier to map out parameter space. And you notice here is I think the second stiffest direction and the sloppiest direction. And you can see that one of them is much tighter constrained than the other. What you haven't noticed is that these axes are not the same. I do this every time, and nobody tells, oh, I noticed. Anybody notice? Okay, this is varying a factor of 1,000 less than this. If I stretch the horizontal axis out to make it match this vertical axis, it would be 1 kilometer long. 1,000 to 1 is the aspect ratio of the human hair. 1,000 to 1 corresponds to 10 to the 6th in eigenvalues. So I'll show you some eigenvalue plots later. But the eigenvalues here span an enormous range. Some combinations of parameters are much more important than others. Everyone following so far? I'm going fast. I'll slow down when it gets really complicated. Here are 17 models. This was in the olden days where systems biology was new, and everyone was excited about not HTML, but nuts. I've forgotten. It's a standard language for writing systems biology models. SBML, Systems Biology Markup Language. And we implemented our own version that would read all these SBML files and would run them all. And here's the model I was just showing you. Here are the eigenvalues. And you can see each of these eigenvalues is noticeably bigger than the others. Notice it's a log scale. So each of these is separated by roughly a factor of 3. There are 48 eigenvalues, 48 parameters, and 3 to the 48th is a very big number. All of these systems, well, I'm not showing all of them, they go all the way down here. All of these models, we took all of the models that had any statement about what they thought the experimental implications were, and we made up experiments based on running their models, and then asked how sloppy they were. And all of these have enormous numbers of directions that really didn't matter. We then pursued a little bit of, there's the whole field of systems biology that talks about robustness, and we tried to argue that most of these models that are used to justify robustness are really just sloppy. There's neutral spaces in evolution that make use of the sloppy directions so that they can sort of randomly mutate without changing behavior. Lots of biology comes out. But this is fundamentally not a statement about biology. All of this sloppiness also happens in other systems. So here's the cell signaling network I showed you. Here's the radioactive decay that clearly isn't biology. These are the eigenvalues of a variational Monte Carlo, the variational wave function used for quantum Monte Carlo by my colleague Cyrus Umrigar, and you have, again, equally spaced in log over a gigantic range. So this is the most accurate quantum calculation for ground state energies. This is the cosmic microwave background radiation. I'll come back to that. So this is, at our universe, you can ask how the different linear combinations of the dark matter and dark energy and Hubble constant vary, and they're nicely sloppy. This is the diffusion equation and the Ising model. I'll come back. So this is renormalization group, and this is continuum limit, the two key tools for getting emergent behavior out of in physics. This is a model of how meat oxidizes in Europe, where they won't let you put carbon monoxide in the package to keep it red. And this is the accelerator at Cornell. As you change the magnet strengths, how the beam gets screwed up. Okay, now I'm going to shift gears. I've argued to you that most multi-parameter models out there are controlled by only a few degrees of freedom. I want to now shift to think about what control means. The distribution of possible predictions forms a surface in a high-dimensional space. So if I think of my fitting exponentials problem, but I only have 2 exponentials, and I only have, I don't allow the amplitude to change, that's a very simple model, and it sweeps out a 2-dimensional surface in the space of all possible predictions. And that 2-dimensional surface I'm drawing here with 3 particular data points, 3 times y1, y2, t1, t2, and t3, giving results y1, y2, and y3. And you can see here, this is the cost surface of fitting those 3 data points with my 2 parameters, and you get these canyons and a plateau and things like that. The things I want to illustrate is that this model manifold has boundaries, that none of my decays can, the smallest that theta can be is 0. I'm not allowing exponential growth. The biggest it can be is infinity, at which point this just changes the first point and ignores all the rest. And there's another fold line where theta 1 is equal to theta 2, which has no particular importance, but the entire behavior is described with a bounded model manifold. And these edges will turn out to be important. Another thing I should say is that there's a natural metric on this model manifold, which is how much you need to change the parameters to have a noticeable change in behavior. Okay, and that you can work out is just the distance in this embedding space. So this space is got, if y1, y2, and y3 have all the same error bars, then distance in this space is proportional to how much and that gives you a metric in the original parameter space, which is given given by the inverse of the Jacobian taking the parameter space into the data space squared. Okay, so this metric is precisely the chi-squared I was showing you before, the cost function. So the Hessian of the cost function is this metric. So when I showed you all those eigenvalues with equally spaced, those were the eigenvalues of the natural metric at the point where we were at the best fit point. Have I lost people yet? Time for questions. I normally go much more slowly. Yes?
The upper limit is infinity. What makes this bounded?
The upper limit for a decay constant, I can't have theta bigger than infinity. But the behavior, if theta 1 is infinity, then yn is just given by 1 exponential and not 2, except for the time point 0. Yes?
Just infinity doesn't mean bounded, right? It's an
infinity in parameter space doesn't make the behavior change.
The behavior is bounded.
The behavior is bounded. This is the behavior space. This is the answer for these 3 times as to what the prediction for y is. Yes?
How do these distribution of eigenvalues you see, have you compared to the random matrix models predictions for these kinds of things?
I will get to, I should address that. In the past, I've told you, we spent ages, I thought of as a waste of time, trying to figure out what random matrix class it was. None of the traditional random matrix classes have equally spaced and log, they give you just equal spacing. And we worked and we concluded that even the ones where you multiply the matrices rather than add them, that did give roughly equally spaced and log, they were a different universality class. Very recently, and I'll mention that later, we think we now have a guess as to what might be the universality class, which is a combination of Vandermonde matrix and the Wishart distribution. Yes, that's an interesting and important question. Yes, we spent a long time fruitlessly on it, and then we stumbled upon what might be the answer, but it isn't working yet. One more question, yeah.
These are all linear combination of parameters. What about other combinations that are not linear?
This is the nonlinear manifestation of the linear eigenvalues of a local metric. So the linear combinations of parameters I was telling you about, if I take, this is not a particularly sloppy model. It's only got 2 parameters, and it's when you add lots of parameters it becomes sloppy. But if you look at the metric tensor at this best fit, it's got 2 eigenvalues. And those 2 eigenvalues tell you roughly at this point how rapidly predictions vary as you move in these 2 directions, these 2 linear combinations, the 2 eigenvectors. And what I'm trying to do here is move beyond those eigenvalues to the geometry of the whole space of possible predictions.
Right, but my question is, how stiff is the direction y squared plus y1 squared plus y3 cubed?
All I'm saying, what I'm trying to say here is that this manifold encompasses the entire nonlinear response as I change the parameters everywhere. I think at root, that's the answer to the question you're trying to ask. That if you give me a path in theta 1, theta 2 space, no matter how complicated, I can tell you what it behaves like just by mapping it into the space. Now, what I'm going to tell you is that this model manifold, which here looks it's kind of interesting and warped, and looks like a manifold, but it's not very sloppy. Sloppiness will be associated with the fact that at some point, one of these directions is got very little change in behavior as I move the parameters a bunch, and another direction will have more change in behavior as I move the parameters a bunch. And the ones that don't change in behavior as I move them a little bit are going to be associated with thin directions. And so the fact that I've got some directions that are thousands of times more sensitive than others will mean that I have thousands of times longer axes before I get to infinity. And this is supposed to be illustrated by these 2 pictures. This one is very clear. This one is a little more complicated because we haven't coarse-grained it all. But this is the diffusion equation, and you can see that it's got 2 directions that are kind of extended, but are very thin in the 3rd direction. And this is fitting exponentials, where I spent some years back, I took this from a PowerPoint and I put it in Keynote, and I had to change the format, and I spent several hours trying to slow it down. I'm sorry, it's spinning around a little fast, but you can see it's very thin. This is quantifying that I'm taking here the widths of the model manifold along the geodesics corresponding to the local directions at some best fit point along the different eigendirections. And then here are the square roots of the corresponding eigenvalues. So when I told you that the eigenvalues are equally spaced over ranges bigger than 10 to the 6th, this is telling you that corresponds to a model manifold that is spanning it has thinner and thinner directions down to square root of 10 to the 6th or 10 to the 3rd. Another thing I should say, we call these hyperribbons. Hypercube, hypersphere, hyperribbon. A ribbon is something that's thinner than it is, its width is smaller than its length, and its thickness is even smaller. And this is just taking that to higher dimensions. So I've now tried to take sloppiness, which seems to be ubiquitous, and turn it into a differential geometry problem. And I've associated it with the hyperribbon. What I haven't done is explain to you why it should be a hyperribbon. And that's my next job. And I'm going to give two different explanations, and one of the outstanding puzzles is what the one explanation has to do with the other. I'm going to first give the systems biology and then an accelerator physics kind of explanation, which will be in terms of interpolation theory. And then I'll give the normalization group and continuum limit physics kind of emergent phenomena explanation. And both of them are convincing and interesting and sensible and very confusing why one is related to the other. So think of a simple model where I'm looking at the time series of some property. So theta will be some set of parameters, and my prediction is just the behavior at different times, just like my fitting exponentials problem earlier. But I'm not going to tell you what my models are. Who knows what family of models I have. All I'm going to say is that my function is analytic in the control parameter time, not in my thetas, not in my variable parameters, but just in the control parameter. And I'm going to give it a radius of convergence R. Now, suppose I now have taken data at a few data points. This is interpolation theory. I can ask how big a range of how big is my possible range of errors given a curve has to go through those points and the nth derivative is bounded by r to the minus n times n factorial. And that's a theorem in interpolation theory. It's actually kind of a nice, beautiful theorem. It says that the range of possible behaviors is given by the polynomial fit to these data points. So that would be a third order polynomial, which has 4 arbitrary coefficients that you can tune to go through those points, plus or minus a term which is a fifth order polynomial, fourth order polynomial times the bound. Okay? Now, if you look at this formula, if the t's are kind of close compared to r, then you can combine these to see that the range, the separation of the times divided by the radius of convergence to the mth power tells you the error bar. Now that's sensible. What does this have to do with model manifolds? Well, remember, the model manifold is a space of all predictions in the theory. So here I've taken a model manifold, and I've confined the model manifold to those points that pass at T1 through this point, at T2 through that point, at T3 through that point, and so on. Each time I take a data point, I'm slicing the model manifold. Each coordinate of the model manifold is a prediction at a given time. Each time I make a measurement, I'm slicing the model manifold, and I'm saying, of all these various values, I'm picking this one. And the range of possible other predictions is the span of the remaining degrees of freedom, is the thickness of the model manifold. Yep?
Jim, I'm a little lost here.
Yep.
You do this interpolation for every set of thetas?
I'm claiming, first of all, if my models have a radius of convergence, and this R is independent of theta, okay, the theta being the parameters, so I've got, sums of exponentials or Gaussians or something, and I limit my polynomials or exponentials or Gaussians, so that their time dependence has a radius of convergence r.
Okay, so the thetas are fixed.
No, the thetas, no matter what the thetas are, I'm going to insist that the model has a certain radius of convergence.
Understood, but when you make this picture, you're fixing the thetas and letting t vary.
The black line is a fixed set of thetas with t varying. The red line is a set of all possible model predictions that where you've tuned enough of the thetas to pass the model through these 4 points. So I'm imagining there are more parameters than I have data points. If that makes sense.
No, it doesn't, but I'm going to be quiet.
Other questions? This is a cool part. I like this part. I like the fact that I can draw a curve and say these ranges are getting smaller as you add more data, and that means that my model manifold is getting thinner every time I slice it. And that makes it a hyperribbon, because what is a hyperribbon but something when I slice it in some random direction, I lose the long direction and I only get short directions left, right? Good. Other questions? You're all claiming to have deeper insight than Bob. All right.
Wait a minute. You just said that you're going to fiddle with the thetas and get the red lines, and they go through your points, but not through the other places.
So this is the bound of all possible answers. So any member of my family of theories cannot produce a prediction bigger than this or smaller than that at that time.
How do you know that you can, how do I say this? You have assumed
I've
that
bounded
there's another set of thetas that goes through those points. That's what the red line.
I've got 10 free parameters and only 4 constraints, so I can have a 6-parameter set of possible answers that I can then vary and get. Yeah, got it. He's getting it. Yeah, cool. So now, recently, this is Catherine Quinn's work. I haven't mentioned the names of all the people. I should. I get enthusiastic about telling things, but Catherine Quinn has been the latest person who's been one of 2 of the latest people who've been working on this, and she's done some really cool things recently. So this, you can work out from the same argument with a slightly different twist. You can work out the space of all possible predictions. And then you can take the fitting exponential, or she can take the fitting exponentials problem, and make an ensemble of different predictions. And so this is this ellipsoid, this very flat ellipsoid, is the bound of any theory with a radius of convergence r. And this is the space of predictions that you saw that rotating wedge before. Of actual behaviors, it's pretty good. It pretty much tells you what's going on. And this turns out to be related to something called the van der Waals determinant. That the fact that your bounds above and below are given by doing the best fit polynomial. Then if you take the derivative of polynomials with respect to monomial coefficients, you get something called the van der Waals matrix. And if you assume the thing has a Taylor series, then you can use the van der Waals matrix. It goes on like that. And your statement earlier is this random matrix theory. We think we can take an ensemble of things and factor out the van der Waals matrix and maybe get actual behavior of the eigenvalues. But it's, in a sense, I'm more interested in bounding the model manifold, the set of all possible predictions, and this does that. It's very cool. And that's also, the random matrix theory is also Catherine's work. So this is also Catherine's work. All the things I've been telling you about are least squares models. We were sort of saying, okay, you can do things other than least squares, you can have long tails, and it's just details, and the statisticians can handle that. And then we started doing things like the Ising model, and I'll tell you a little bit more about the Ising model in a moment. And we got confused, because the Ising model, for an n by n lattice, for a 4 by 4 lattice, it's giving you a probability distribution of all possible snapshots. And it wasn't clear how to talk about the distinguishability between snapshots. And here, this is the cosmic microwave background radiation. You remember the cosmic microwave background? There's this picture with little fluctuations, and then they pull out the angular correlations. How many of you have seen this before? Okay, so I'm not boring everybody. This is our universe. This up here is a universe where you only see the first half of one peak. And the universe here, the peaks just die away really quickly. And this is the model manifold, but this was really hard to find. Meaning, well, not really hard. Let's say nobody has ever done this before. So these are probability distributions, and the natural metric in probability distributions is normally the only thing that people normally do. Gives you a projection that, okay. Isometric embedding. What do I mean by that? I want two models to be far apart based on how hard it is to tell this model from this one, so that the G mu nu is correct. But I'm willing to put it in some high dimensional space. If I just look at the correlation functions here, it's not a linear embedding. It's not isometric. It's a non-Euclidean embedding, and I want it to be embedded linearly in a flat space. The Ising model, similarly, I can take the square root of the probability distribution, and then it is an isometric embedding, but it's really curved, and it gives you meaningless embeddings. And so the root problem is that you have too much data. That if you have two data points in the model manifold, in the cosmic microwave background radiation, you change a parameter very much, you have so much good data that the two become orthogonal. And so what Catherine did is she took the limit of zero data using something called replica theory. I won't go into details, although I'm delighted to share with you anything after the talk. And this replica theory is well known to those who know it as being voodoo. And what voodoo means is it gives you things that sometimes work and give you beautiful pictures, and sometimes they're just really inscrutable. And in this case, the inscrutability comes from the fact that since you're extrapolating to zero data, in some sense this is a manifold embedding in a zero-dimensional space, and it's flat, but non-Euclidean. It's a Minkowski space. So one of the three directions here actually is time-like. Other than that, this is great. Okay. Say again?
So what are the on the left one, like the space of all possible universes?
So in the space of all possible universes, I've illustrated this long part of the banana by drawing these three pictures. If you do the short part of the banana, you can see some characteristic features too. The color is the Hubble constant, turns out. But you can draw other colors. We just picked one that kind of looked nice. Other questions? Here, the color has to do with the magnetization. So this is high temperature. This line is low temperature. This is all spins down. This is all spins up. High field in the two directions. Yeah.
Just to get back on the axes thing. So is this like you're varying omega?
Oh, what are these axes? I can say that. These three axes are the three biggest principal components. Principal components are the way you look at the long and short directions in things that have very strongly anisotropic axes like hyperribbons. And principal component analysis is a big deal, and it's just amazingly convenient that this extrapolation in replica theory gives you the information you need to do principal component analysis. It's very cool. And this is the kind of wacko thing that only physicists would do. So I'm imagining that the whole statistics community will be both skeptical and it's not a surprise that they didn't do it first. Maybe they did. It's a big literature. Okay, so one more thing. Nuts. I flip back. I flip past this one. This is, you remember I promised physics? Here's physics. Here's the diffusion equation. You recognize random walks, become a Gaussian. Here are the, you just take this thing and quantify it and look for the sloppy eigenvalues. Here, after one time step, basically you can measure all of the basic rate constants, hop right, hop left, hop right 2, hop left 2. You can measure all of them, so there's no sloppiness. But after 6 time steps, you get a very broad distribution of eigenvalues that it basically looks like a Gaussian independent of what your original hops will look like. Okay, and that's not a surprise. The continuum limit, all that matters in a random walk, is the diffusion constant. Here I'm taking the Ising model at its critical point. Here I'm looking at the eigenvalues away from the critical point, and you see this interesting cusp structure but only 2 relevant eigenvalues and a bunch of irrelevant eigenvalues. And here are the eigenvalues as a function of coarse graining, where, again, just like here, if you don't coarse grain, you can measure everybody. This is only a factor of 10 to the, a few decades. But as you coarse grain, you lose information about the irrelevant degrees of freedom, and it's only the relevant degrees of freedom that are maintained. All right? And we call this parameter compression. Yeah?
They seem to bundle, and you've got that indicated with colors there too.
Say again?
Oh, the eigenvalues are in stacks?
It's known by those who know it that the eigenvalues clump in this way. Okay. And I'm not sure I'm one of the ones who know it, so I don't have an but Ben explained that this was standard. Ben Machta and Ricky Chakra were instrumental in this. Ben is now an assistant professor at Yale, and Ricky is now working for Lyft. Archishman Raju has been working on this in one of his various projects. And he's been thinking about the renormalization group and the beta function and how they change the metrics, and he's deduced one interesting fact that I just wanted to mention, partly because he's a cool guy, that it turns out, you know, relevant directions grow under coarse graining and irrelevant directions shrink, and different relevant directions have different amounts of growth. Well, if you measure things not in the space of parameters, but in the space of results, distinguishability, it turns out in some ways the relevant directions all grow by the same amount, or in other ways you can think of it, they don't grow at all, they just stay fixed. It's just as easy to measure the deviation from TC and the deviation from zero field. It's just as easy to measure them on a 1,000 by 1,000 lattice and on a coarse grain 1,000 by 1,000 lattice that's only 10 by 10. But all of the irrelevant directions shrink under coarse graining. So here's a relevant direction, which is supposed to be the same after coarse graining, and here's an irrelevant direction that's supposed to be shrinking. Comes out of the math. Okay. Last thing, how am I doing on time? 10 more minutes. Last thing I wanted to really say has to do with work that I was not involved with. This is Mark Transtrom, who's now at BYU. He has personal reason to be at BYU, but he's doing great, and he's doing a lot, and this is one of the things he did. He wanted to understand about coarse graining. I used to say, when people would say, can you coarse grain these models if only 5 directions matter? Why do you have all these parameters anyway? And I would say 2 things. One thing is the sloppy directions that you'd like to get rid of are just random combinations of parameters. It's not clear how to get rid of them. And the second thing I would say is you really don't want the coarse grain model if you're a systems biologist. You want to be able to say, what happens if I change this parameter this much? And Mark just fixed that. First thing he noticed is this is the sloppiest eigendirection, but he developed this technology of doing geodesics along the sloppy directions. And when he took the sloppy geodesic and went to the edge of the model manifold, it became a simple direction. That this end of the model manifold is associated with a simpler model. The fundamental statement is a multi-parameter model has embedded a lot of simpler models where you take certain limits. So this particular direction took you to had one of these saturable reactions, and you could ignore the saturation constant, getting rid of one parameter. And then he would take the next sloppiest, he would start on here, and he would take the next sloppiest direction, and you would get a hypercorner of the model manifold, which gets rid of another parameter. And he would do that, and he would do that. And so he started with 48 parameters and 29 differential equations. And each time he simplified, he would get rid of one parameter. He would get rid of something in this diagram, one of these arrows or something. And he would get rid of, and he would get an explicit new set of equations, writable, downable in terms of his old parameters. And so after 36 such iterations, he got this model. Notice how much simpler this is. This is pretty clearly a negative feedback loop and a side branch. That's all it is. And this is actually how Rick Sarione described this to us the first day. His intuition is just implemented now but by math. Notice the eigenvalues. They were spread over 11 orders of magnitude, and now they're pretty tight. Notice the equations. These are, relatively simple equations where each of the new parameters is explicitly writable in terms of the bare parameters. This doesn't make this the correct model. It's sort of Occam's razor. It's the simplest model. It's a simpler model that describes the data, but not all of these model reduction steps have to be perfect. But but it is a coarse-grained model that captures something that's compatible with reality, something that's a simple, comprehensible model that's one limiting case that explains all the data that you could then build on to think about new experiments. Okay, so I'd like to conclude by being grandiose. Okay? I think lots of things might be coming out of this. You don't have to believe me, but you should hear the things I think might be related. One thing is principal component analysis. Some of you have heard of it forever, and some of you have never heard of it. It's a way of taking data from whatever and pulling out the things that vary a lot so you can ignore stuff. And I think the reason it works in many cases is that the data is coming from something where the model manifold is a hyperribbon, where only a few things mattered. Very popular in biology. Least squares fits. There's something called the Levenberg-Marquardt algorithm that we've been using all along, and we didn't like it, and so we thought about it, and we can figure out why it works using our differential geometry. It's a geodesic motion on the model graph. And we can find better Levenberg-Marquardt algorithms using this kind of method. So this geometrical picture tells you nice things about why numerical methods will work or won't work on sloppy models, which are most of the models you are fitting to data. I mentioned before that robustness in biological evolution and neutral spaces and evolvability all might have something to do with sloppiness. It's not complete because the mutational motions are not continuous, they're discrete, and there's complications there, but it certainly feels related. Pattern recognition. Big data, which is kind of computational pattern recognition. Are they looking at low-dimensional structures like this? I should say we've worked hard to think about whether big data is basically generating a hyperribbon-like model manifold, and after torturing my graduate student for a long time, she convinced me that the set of all possible images that you could reconstruct from a neural network trained on handwritten digits was basically a big furry ball and didn't have any hyperribbon structure. So I'm willing to put big questions that I think the answer is no. But why is science possible? Things are complicated on the microscale. Things appear simple on the macro scale. We understand that at critical points. We understand that for things like diffusion that have continuum limits. We don't really understand that in climate science, in economics, in biology. That we still do theory. We still make up simple models. In systems biology, we know the models are wrong. That every few years, that pathway I showed you, the MEC and ERK it's got 2 or 3 different names, but for the next few years, every couple of months, there would be another Nature Science article saying, we've discovered another thing in this pathway. And I think science is possible because there are coarse-grained descriptions that come out of this sloppiness in some way. You can get very different models that span the same hyperribbon kind of space, maybe explaining why. And so I would like to think that there's some sense in which much of the way we understand the world, much of the way we guess about what happens in the world is based on the fact that the world's emergent behavior is in a sense low dimensional. Thank you very much.
Back to the plot of the universe, where you had different colors. That plot, yeah, on the left. So you said that the three axes are basically first, second, and third eigenvalue after you do the PCA. What are you doing? First of all, are each of these points independent parameters?
We tried to sample the model manifold using Jeffrey's prior, and we went nuts, and in the end we set a hypercube of reasonable parameters, and we took all the edges, and these are all the edges of the hypercube.
Okay, so each of them is a theta of that hypercube?
Yes,
okay.
It's a set of parameters, yeah.
So for each theta, I just want to functionally get an understanding. For each theta, what are the data points that's going into the PCA?
So this is a two-dimensional projection of the first three principal components of a vector which in principle has an infinite number of components in a zero-dimensional space. Oh, geez. I think if I just shut this exit box sync, yes, go away, yes, okay. I mean, you ask a question that I don't have a good answer for, because but on some level, if this was a traditional model manifold, as opposed to our replica theory model manifold, then what you'd be seeing is just a three-dimensional projection of the 2,000-dimensional vector giving this probability distribution. You know, all of the 1,000 dimensions. Each angular momentum channel has a different prediction for its brightness. And that would be a 1,000-dimensional vector, and this would be the most important three directions in that 1,000-dimensional space. So let me answer that. That's the simple answer, and then I've garbled it because this is a probability distribution, and that's a non-Euclidean projection, and we've done this sneaky thing with replica theory, which makes it very confusing. Yeah?
Related to this replica theory stuff, the timeline direction that comes out, is there like a reason for which combination this is the timeline direction?
Got me. Yeah.
You talk about how biologists will kind of discover every couple of months something new in that pathway. Is there anything you can take from this and reverse that and give them a hint of like something that's incomplete in the model and proposed measurements they can make to try and discover something new?
There's optimal experimental design. And one of my students wrote his thesis on optimal experimental design. And there was Rick Sarion's group was studying blah, and at some point the question was what experiment should they do next in order to not reduce the uncertainty in the parameters, because we think that's stupid, but to reduce the uncertainty in the things they couldn't measure that they wanted to understand. And he did the optimal experimental design, and Rick Sarion came in, and he had all his transparencies, and Rick said, I think we should measure this at around 10 minutes. And out came out the optimal experimental design at about 10 minutes. And this sloppy model analysis was necessary because you weren't interested in the parameters, you were interested in the behavior. Yep. Oh, sorry, he's in charge.
You're in charge.
You can just go ahead and say that first.
In the second last slide where you showed that how using the geodesic method, someone was able to reduce from 48 parameters to only 6 parameters. So finding those geodesics would require one to know the metric, and then to know the metric, you need to know what the model or what the ansatz you start with. So I guess
measuring the metric you can do pretty conveniently for most simple models, just by looking at the Jacobian of how much the data points change when you change the parameters. Yeah.
Okay, so you don't need to know you don't need to have a theoretical model as long as you just have data points. You could, from the data points themselves, you can know what the metric is.
You're saying if you had an experiment
of the theory is, or just the data itself?
you would have to be able to do a lot of experiments. You know, you'd have to change each of the parameters and each of the parameters just to take one step in your geodesic. But it's not impossible.
Yeah, because a priori, usually you wouldn't have a model, say. Maybe,
if you're an experimentalist, if you're a theorist, we always have a model. Yeah.
So Jim, I am massively confused about the mix-up here between epistemology and what you can know on the one hand and what nature does on the other. Now, so I'm groping for a little clarification here because I think these things are different. If you annihilated all the people tomorrow, nature would still be doing its thing.
Yeah.
So nature does not do things because we think it is. It does things because it does them. Now, when we're doing epistemology...
This is one of those big questions we were talking about before. Yeah. Why is nature comprehensible to us? Yeah.
Well, so your examples of models are an epistemological exercise where the premise is rather fuzzy. I'm really confused about whether the zillions of equations you're premising are known to be correct and you're trying to account, or they're just wrong, and it turns out the bundle of equations have insensitivities, and so the mistakes don't matter.
But that's okay. Yeah.
Well, is that what we're talking here? We're talking about falsifiability, predictability from things that are known to be true, or are we talking about things that are not known to be true that you're trying to understand, that you're trying to infer from facts, and you don't have enough information to do it?
I mean, I don't want to get too dogmatic because, of course, we don't understand the systems biology in the cell, and we really kind of do understand magnets and accelerators. And the same stuff is happening in both. We know why in the accelerators, and we don't in the systems biology. So I don't think the message I have is really tied to that. But I can say that Mark Transtrom, after our paper saying this model is sloppy, it's got giant ranges of parameters, you can't possibly measure the parameters, the systems biology community went nuts and said, yes, I can measure these parameters. And one group, which was really quite cool, Tidor, I've forgotten if he's the lead author or he's the person at MIT who led the group. I think it might have been the second. I'm embarrassed, I should know people's names. Actually computationally worked through our model and found a set of experiments he could do with only 100 times as much data that would pin down all the parameters within 25%. And that was very interesting because by carefully choosing the experiments, he got many fewer data points than our naive estimate would be, but it's still 100 times as many data points. Instead of 63, he needed equivalent of 6,300 data points. The other statement, though, is that Mark points out is even if you could carefully design a way of finding all the parameters in your model, you would discover your model was wrong anyway. That there are assumptions that go into the models, there are separations of timescales, there are side reactions that hardly matter but matter a little bit, and if you carefully design something your experimental protocol becomes so tied to the particular model you're trying to falsify that you're, all you'll do is discover that your model parameters aren't right.
Am I allowed to ask a follow-up question? Okay. Jim, in physics, we know why this is, okay? It's a physical phenomenon.
Yep.
Okay? It isn't by logic, okay?
Yep.
It's like thermodynamics emerges because it just does.
Yep,
Okay?
yep.
Now,
Here I am. Emergence is a big thrust of intellectual endeavor in physics. And here I am contaminating emergence by sticking in the systems biology stuff.
Wait,
Just give it, yeah.
wait. Biology is engineering, okay? It isn't physics, it's engineering. It's making machines that do things, okay? And the question is
Accelerator building, yep.
whether the principles of physics that we're talking about that make things simple are also necessarily operative in engineering. In other words, is you're thinking about this mathematically, we make a mathematical
I can say not only do I think they're appropriate in engineering, but we use them to build accelerators, which has got to be one of the biggest engineering projects that we do. That's not true. Nobody's used it to build an accelerator. We have used it to tune the accelerator to see if we can get better emittance. Yeah.
Well, the follow-on question is it possible at all? Is it possible that you can engineering things without this principle? In other words, is it not only sufficient, is it also necessary?
So I would say if you look at one of those clocks with all those gears in it that do this and that and the other thing, I think it would be.
There's more than one way to make a clock.
If you increase the radius of this gear and decrease the radius of that gear in some way, I bet you could get sloppiness. But if you start removing teeth or making something jut out differently, it would break. That it's not true that every humanly designed thing is got sloppy directions. I would agree. That the magnets in the accelerator are something where the beam is going by and it's dealing with the compromise of lots of different things. It has to be a model. So the distinct
was whether you can make engineering at all, even in principle,
if it wasn't sloppy.
If it weren't for emergence.
Oh, that's a possibility. We should talk offline. It'd be fun.
Maybe one more question. Yeah.
Thanks, this is fascinating. Can you define explicitly sloppiness in relation to your questions? And I'm asking this in the context of developing a realistic virtual Earth universe that would be at the cellular and atomic levels that would potentially be conceptually Google Street View with maps Earth with time sliders. So you could have all species emerging in this unfolding realistic virtual Earth universe. In terms of the differential equations, differential geometry that you would apply to such an environment and shaping, it's kind of a machine. What is sloppiness yeah.
Sometimes you get asked a question, you try and transform it into a question you can answer. I don't know anything about it, but people ask a lot, do I need 6 orders of magnitude in eigenvalue, or would 5 be enough? And what does it mean to be sloppy? And first of all, the eigenvalues are not trustworthy. You can do nonlinear coordinate transformations and change the eigenvalues. But the geometry of the model manifold being in prediction space is more robust. But our pragmatic thing is if the eigenvalues span more than 6 orders of magnitude, we don't think that that's an accident. We think that's probably real. And we would claim that we should be able to understand it.
One last question here. So if you, for whatever in your model, you're missing a parameter, just not including your model, that where it is stiff in that direction, how robust are the manifolds that you create from that? So if, as it turned out, the real way that the better model would work, you're missing a stiff parameter, how, in your prediction, how robust does the...
Let me translate that into a question I can answer. In that 48 parameter model, there were lots of versions of that model that didn't work. We built that model. I said, well, we typed in the equations and it worked. It didn't. We ran the model. We thought really hard. We figured out that this couldn't possibly work. We would talk to our systems biology person. He would say, oh, yeah, you need to do this. We would add that, and then we would come back. And then for a long time, we couldn't figure out why it couldn't work, but it didn't work. And then we realized that it was stuck in a metastable state. It was stuck near the edge of the model manifold, and you needed to drag it and stick it in the well. No, it's not true that sloppiness allows all models to fit data. It's quite the reverse. You have to have something right about your model in order to fit the data at all. That helps.
All right, thanks. Thank you, Jim. There's a dinner for graduate students and some other people, and if you guys want to come down and talk to me, we'll